Alright, how we doing today? Doing good? Alright, cool. So for today's lecture, our continuation of last time, we're going to go over the Laplace transform, the state space equations, and actually maybe should I do this practical. So today we will go over some state space equations, and I'll be helping you guys out with this assignment that I have to show you guys for today. The assignment's going good. Hopefully everyone started. Let's see. Let's go over that. So from the last lecture from Friday, we went over the first half of the assignment, and it wasn't that bad. We did an RC filter, as in, let me show you guys this. Nope, not that one. There we go. This where we took our, let's draw it again, plus minus this RC. Here's I'm gonna call this one X of t, and this is Y of t. And then we solved for our equations, and if you guys remembered from last time, we figured out we can represent this differential equations by, let me do this, by the following. dv, or should I do this, dy of t dt plus 1 over rc y of t is equal to 1 over rc x of t. Remember that? From Friday. So, if you remember from what I was trying to show you in this assignment, one thing that someone's been telling me is that, hey David, what is this system right here? Like, what are we doing? And point is, okay, if you look at what we did last Friday with this system, all you got to do is just, add new numbers here. Remember, if you wanted to do, actually, let me just do this example quickly. If you guys wanted me to try, put this right there, put this right here. And if you wanted me to tell you, okay, so suppose you had something like this, actually, I'm gonna write it shorthanded, y double dot plus, plus a1 y dot plus a0 y, actually a0 is always 1. This is probably something different. I'll think about it. Actually, no. a2, a1, and then a0, because we're looking at derivatives, sorry. Y, which is equal to, let's just put b1 x dot plus b0 x. Right, remember this stuff right here? Let me think about this. So if you wanted to represent this as a Laplace, the little rule that we came up with is, okay, depending on dny dt, you can convert this into dn. You can convert this into s of s of n ys, right? Minus s n minus 1 y t is equal to 0 minus and dot s to the nth power minus n d, okay, we're taking a derivative there, dy of n minus 1 d t n minus 1 t is equal to 0. Remember that stuff? If you wanted to convert this into something like this, you'll see the following. Do we have initial conditions in this one? Okay, so in terms of it, okay, so for this system, which is your homework, since we're just looking at this system right here, let me just highlight it right there. We have no initial conditions, so if you think about it, here's this y, t is equal to 0, here's this. Just imagine this goes away, and then all you're left with is just this pattern. This right here is your rule to memorize. Okay? This is like no initial conditions. These are ICs. initial condition. So if you wanted to convert this into the Laplacian domain, so Laplace, you'll get the following: s squared y of s plus a1 y of s plus y of s is equal to b1 s of x of s plus b0 x of s. There we go. And then you can just try to figure out how to get h of s, which is equal to y of s. Oh wait, you guys can't even see that. There you go. X of s. All right. And then this same process for putting it into, come on, where's my mouse? There it is. Into the little code I gave you guys, this right here and this, then it should be the same process. I would assume everyone can do this. This is really straightforward. This right here will draw you a z-plane graph. Shouldn't be that bad. Residue function. Okay, maybe I'll show you guys that. Okay, here we go. Let's just go over Matlab. Shouldn't be that bad, right? This is what we did last lecture. But I didn't put that there. Let's just copy it. Okay, copying. Exercise 3. Yes. Go. Put it right here. Lecture 13. There we go. Oh, what's this? What did I do? Step, freak, doot. Log of 10. What is this? Oh. I know what's going on. It doesn't like that because I gotta flush this thingy out. There we go. Copy. Okay, might as well copy the entire assignment, whatever. There we go. Boom. All right. Well, one edit I'm gonna do. Just call this one something. Step. There we go. Because there's a function I need to tell everyone at the end of this assignment. So running this. Step. There we go. Boom. There we go. Remember that stuff? We were doing that? Oh, yeah, pretty easy. Here's our little pull for our RC circuit, right? Let's see. This equation here describes our RC circuit. Let me write that right here. Your transfer function. All you do is just brute force the numbers. You can do this or you can do this. This is the same way too. Let me do this. 1 divided by tau, where tau is this RC constant. And then this is your total transfer function. This is power. Don't forget that. Run. See? Not that bad. So the same procedure right here. What are you going to do for your assignment? You're going to, let's see. You're going to plug in whatever you find here from here to here. Whatever is here. And just plug it right here. Simple? Perfect. And then, let's see. Let's just run this for now. Oh, wait, no. Beep, beep. It's not going to run, obviously. All right, and you see this right here, right? Okay, this is probably not making sense for some of you guys, but I'm going to just take it into the positive Fourier frequency domain. Make this 20K. So if you remember from last time, I gave you guys a system where not F3dB, we're going to call it S3dB, is equal to 1 over, I think it's like 1K or something like that. The pole is at 1K, something like that. I think so. But then if you think about, actually no. Point is, I gave you guys some RC circuit, and it gave you a pole of 1K. And let me see, actually. Okay, I'll give you guys the formal one. This is messy. Next page. Drawing that same circuit, the RC filter. RC filter transfer function. You got h of s is equal to, let's see, some people know it as 1 is equal to 1 plus src, right? Remember that? Which is also equal to 1 over rc, in a form we all know, s plus 1 over rc, right? Where this right here, s pole, or s pole, whatever that is, 1 over rc, there you go. And then we realized that this right here is a time constant, which is equal to 1 millisecond, but the inverse of 1 millisecond is, yeah, this 1k. Simple. That's our pole location. See? And then running this again, and then you can see why it went from 0 DC frequency up to 20k. This E3 just stands for k. And let's make this step. What's a step response? Okay. Let's make it finer. Dot times 0.1. There you go. Does that make better sense? Let's see. So if you go to 1k, which is right here. Oh, let me just increase that size. Boom. See that? What's that? 3 dB. Cool, huh? And then let's go to right here. Close enough. There we go. And what do we have for our phase of an RC circuit at the pole? For our bandwidth? Well, minus 45 degrees. See? The reason why I gave you guys this RC circuit, well, one, because it's gonna probably be on your exam, but two, I want you to guys like try to experiment with all this stuff. Like, don't just do the assignment. Make your own problems. Like right now, like everything right here can just, well, everything I've done with the RC circuit, you can just replace it with other numbers like this. Really, really simple. So let's see. This is easy. This is easy. What does Z-plane do? Let me try to show you that. Let's see. Z-plane. If you guys aren't getting this, then hopefully. Oh wait. Oh, that's something wrong. Okay, run this. Run. Oh. What is that? Oh, that's a different plot. Well, actually, it's the same plot. There you go. There you go. That's your plot. This is using the Z-plane function, I think. Let me see. Oh. Yeah, Z-plane. Where, come on, where it is. Where, if you can see, that right there is our little pole. See? Minus 1k. And then here's our 0. All our poles are on the left side of this 0 marking right there. That's how you'd see this. Hopefully that was a little helpful. And let me see the residue function. So let me show you this one thing. So I don't know if you guys caught it, but I told you how to do the residue right here. The residue function. All you do is just copy paste this puppy right here. I think so. Actually, here are your B's, here are your A's, RPK, and yeah, that's literally it. Where R is your residues, and then here's your poles. So honestly, if you just copy this, actually I'm literally looking at my old code. And this is it. So honestly, if you're not really following these videos or watching my content, then I have nothing. I don't know how to explain it to you. Okay, someone's probably asking, David, just do it for us. Okay, I'll do it. Let's punch this puppy. Residue. Because we're an analog. Okay, paste. RPK. Residue, what's B? Our B's are this. We're looking at our actual coefficients. Don't copy this part. This is S. Don't do this. do this. See, these are our little coefficients. So what did we do here? H Fourier num op num f oh come on num and then h and Fourier. There we go. And then let's run that. Boom. What's going on? Run that. Oh, because okay, whatever. There we go. Same plot. Run this again. There we go. Easy. Residues. And did it plot? Oh, that's because I didn't plot it. Hold up. Figure plot the time domain. Actually, before we do the time domain, remember from our little quizzy thing, we're saying, oh, this right here is our time constant, right? So that means how long for our, if we were to pulse it or do some step response, how many time constants does it take for it to settle? 5 time constants. So if you were to kick this box, what's the impulse response? All you're gonna get is, well, if you just h of t, you're gonna if you just kick this box, all you're gonna see is just kick and then just something like this. Well, okay, if you wanted to, what is the inverse Laplace transform of this? L minus 1 of h of s. All you look at is, here's your residue, and then here is your pole. So that means what you're gonna do is 1 over RC, and then let's use a black marker, e to the, our pole is equal to minus 1 over RC, because that's how you make this go to infinity. The minus 1 over RC times t. But remember, this 1 over RC is equal to 1k. Therefore, we got 1k e to the minus t over 1 millisecond. So what do we see here? So if we kick this RC filter, we just put a delta function here, just where the delta function just is a spike that goes to infinity. Okay, so if we do it to this filter, we're gonna get a value of 1k here, and then after 5 milliseconds should get down to 0. Does that make sense? All right, prove it. And that's where we get the following. Let's here we go. So we're expecting at 5 milliseconds minus 3, and then let's use a precision of let's see, 100 micron, e minus 6. All right, statement is incomplete. Let's see. Oh, the time, and then let's plot h. Perfect. Boom. Am I getting your money's worth? See that? Here's, if you kick this little box, I'll show you. Put an impulse that goes to infinity, it gets filtered out, and then all you get is this value of 1,000, or 1 over RC, and then it decays like this. Here's our hand calcs. Okay, and then here's proving it in simulation. Making sense? There you go, and from that is the first half, and now we're ready for the second half. So let's make this problem 2. So I would assume everyone should hopefully get this done pretty quickly. First half shouldn't be that bad, but the second half is going to be pretty wild, practically. So let's talk about state space equations. So remember with state space equations back in the days where we would oh yeah, we would have some let's think about it. Let's think about it. Do I want to do it analog or digital? Now let's do analog. Where if we were doing okay, actually let me just show you the practical stuff. If we were doing an integrand, like an integral, and we have some dq, some derivative, not that, divided by dt. If we integrate this, then we get the following q of t, right? So okay, so from the last time, from I think it was like chapter 2, 3, where if we were just doing regular stuff, we were doing these dt of like q t dq derivative t. Remember that stuff? This is like normal difference equations. Diff EQs. Remember that? Right now we're gonna do something like this. We're gonna have these derivatives, right? We're gonna analyze these derivatives. These are these next states, and then look at whatever it outputs. These Q's, right? Let me see how I'm gonna explain this. Let's think about it. Maybe I'll just show you by example. So looking back at our RC filter right here, right? Remember this? So I'm just gonna do this practically. Let's get dy of t dt plus 1 over RC y of t is equal to 1 over RC x of t, right? So if we wanted to get it in some form of we're not going to use these differentiators. We're going to try and get these into integrators. So what you're going to do, if he gives you a problem like this, you're going to do the following, where you just integrate the entire thing like that. And then your final result is y of t plus, I'm going to shorthand this, y, right? Is equal to 1 over RC x, right? And now solve for your y. 1 over RC x minus 1 over RC y. Cool, right? So in practice, we don't really build these differentiators. We build integrators. So if you wanted to build this in a direct form 2 aspect, remember how we drew these direct forms? So we would start from the input, right? X of t. Remember the direct form 2, it's had these feedback circuits and feed forward circuits. These one would be in the front, this would be in the back right here. So if we were to model this, we have one integrator, so we have 1, right? One integrator. And then since this right here is a pole, it's gonna feed back the output. Let me draw it right here. Actually, I'll show you something. The reason why I paused right there. 1 over RC, right? You see that? 1 over RC. And that feeds on itself like that. Let me just minus 1 over RC. Better? Cool. So the reason why I paused here, okay. So you see this right here. You see this input, right? All right. So we have our input right here's x of t, right? It goes in here, gets integrated, and then we add it right here, RC, and then we come right here. What does the output see? The output sees a positive input, so here's our input, and then it sees a negative output, so here's our output, right? Y of t is kind of right here. Actually, no. If you see it from here, it makes sense like that. I think so. Point is, direct form 2s are really hard to see, but trust me on this one. Minus 1 over RC, it feeds back, boom. Easy. So now, the reason why I was choking here, this right here is an open for the RC circuit. So in reality, well, you just see this path going down right here. It goes like this, go this, go this, go this. That spreads that way too. That goes that way, that goes that way, and that goes out. Cool, right? All right, so now let's just practically do this. So if we're gonna try and model something like this, right, into this type of system, right, if we're gonna look for the state space equations, all we're gonna do is look at these integrators, and whatever is at the input, we're gonna do this Q of 1, right? And put a dot right there, right? What is the integrate? When you integrate this, what do you get at the output? Q1 of t. Cool, right? All right, so now the next thing we're gonna do is, well, just solve for your equations. So remember, the whole point of the SS equations is to get the following format where we're gonna have some Q matrix is equal to AQ plus B X, and then Y is equal to CQ plus DX. We're gonna try and get it into this format. So all we gotta do is just solve for this and solve for that. Okay. So if we were to look at that problem, let's see. Oh, what's our output equal to? Y of t. It is equal to, so well, Y of t sees this. Well, this right here. So here's Q1 of t. It goes through this 1 over RC. And it's just this, RC Q1 of t. And is that it? And this is an open, by the way. There you go, you're done. That's it. Now let's analyze this, because now we got to solve for this and this. Okay, what is Q1 of t? It's equal to whatever is at the input minus 1 over RC of Q of 1. And is that it? Current inputs, current states? You're done. That's it. So that means if I were to write it in a general format, the way you're used to seeing it, where Q, the matrix Q is equal to, well, since this is just a first order equation, you're just going to get Q1 of t is equal to, what's A? A is just, well, this, minus 1 over RC, Q of 1, right, of t, plus, so this is your A, and then what's our B? We have this input, 1 x of t. Cool. And then our output y is equal to, well, just y of t is equal to, what's our C? Here's our Q1, here's our C, 1 over RC, Q1 of t, plus, well, we don't have an input here, so that means this is 0. So there we go. See, that's our SS equations. Pretty cool, right? All right, now let's just punch this into your Matlabs. So if we were to go back to our little problem, let's do this. SS equations. And let's think about it. Via hand calculations determine, no, not that one. Nope. Oh, draw and label a direct form 2, and then, well, I give you this hint right here. Just solve for that. Use integrators. It makes the problem much easier. Using the transfer function to SS, generate a state space model. So let's see. That you developed in equation 1. Compare this to the hand calculations in exercise 9. So point is, you're trying to solve for your SS equations, okay? You're solving for, this is what you're solving for, right? Now you're going to use Matlab to verify this. How do we verify this is correct? Okay, let's see. So exercise exercise, what number was this one? 9. And calcs. Place pick of hand calcs here. Okay. Exercise 10. Verify in Matlab. Alright, how do we verify in Matlab? And I'm just gonna copy paste this from here. There we go. Boom. Oh, not that. Boom. Look at that, right? And then I put the 0 here because I was doing something weird. And what's this and what's this? Oh, that is from here. See, making sense? So you can just literally just copy paste this down here. And then this is how you use the transfer function to state space. Just put your numerators, here are the denominators, creating SS equations. Now run it. Boom. And then here's your output. Oh, what's that? You see that? Here's our A vector. Minus 100. Not that one. Let me just put that right there. Or 1000, sorry. See that right there? That's our A. That's minus 1k. Here's our B. See that? This B is 1, that B is 1. Making sense? C, 1000, and D, 0. If you get these numbers to match, these A, B, C, Ds to match with your hand calcs right here, congratulations, you're done. You're hallelujah. You can do this and you can hopefully get an A on this exam. That's the whole point of the state space equations. So if he gives you some circuit, like if he gives you, not a circuit, but he's probably going to be pretty gentle on you. If he gives you this, a difference equation, can you get to here? All right? That's literally it. All right? So now the next step is, let's see. Using the SS, the state space equation, frequency response, and squeeze functions, calculate the frequency response. And I would assume probably someone wants to know how to do this. It's okay. This assignment should be pretty easy. This is not a coding class. Let's see. I'm going to copy this. Shouldn't be that bad. Boom. All right, I'm just going to give everyone this. I don't want anyone to suffer. If you're not doing this assignment, then that's a problem. There we go. Exercise 11. No. Frequency response. S domain. Okay, so I'm just calling some random system my system. My system. Okay, and you're gonna punch in your state space equations A, B, C, D. Done. Do. And then this right here is your frequency, or angular frequency. Okay. Remember, we're not looking at F. Actually, let me punch this in. We're not looking at F. We're actually looking at S. So in reality, let me show you. Actually, let me do this. H of S, right? Is equal to 1 over RC, 1 over S plus 1 over RC, right? When we look at just S is equal to J omega, right? This omega is equal to 2 pi F, okay? So that means we're not looking at F, we're looking at omega. So that means this Bode plot, remember these Bode plots? Actually, I should have drawn that above. It's okay. We're gonna see something like this, okay? Here's your 0 dB. That means this right here is S3 dB, should be equal to that 1K, okay? Does that make sense? And if you wanted to get the frequency, well, all you do is just F is equal to omega divided by 2 pi. And then if you're really that OPCPD, just go ahead. But we're just dealing with the S domain, okay? So, back to our code. Since we know our pole is going to be at 1K, I went up to 20K. And then I did this type of step. And here's your frequency response. You just take your system, take your angles, boom, calculate it. Here's power. You guys can fix that. Actually, let's do that. Let's see who's copying this. Here's your angle in degrees. There we go. And then I did this just for you guys to know. Actually, okay, plot. Boom. Oh. Oh, did I use that equation? Okay, I know exactly what I did. So remember that nice little function I gave everyone from the beginning of the semester? Let me plug and chug that right here. Hopefully I can finish this video. I'm gonna go over a bigger review. Functions. Boom. See that right there? So well, this is if we didn't do a semi-log of this, right? But if we turn this into a log version, so you see here is 1, here's 2. We would like to see this in terms of like logs. So that's why I did this. Semi-log x. Wait. Oh. Semi-log x. Semi-log x. So that means we log the x component to get the following. Oh, what's that? What does this look like? Oh, it looks like a Bodhi plot. What's that 10 at 1K right here? Come on, close enough. Yeah, close enough. 3 dB. Easy. And then, oh, what's our frequency right there? Come on. Close enough. Almost 45 degrees. Come on. Close enough. 45 degrees, minus 45. Alright, the reason why I'm doing this RC circuit is to get you guys familiar. Like, this is not a scary assignment. This is like an assignment that you can use in 370. Like, if you can do all of this, like this right here, is all 370. EE370. Okay? If you can do all this, and you can analyze this, like this too, using control... use controls toolbox. If you can do all this stuff in Matlab for any system, then you're literally set. You can do whatever you want. Back in my controls days, I really wish I knew this. So hopefully this computer assignment 5 will carry on with you. So everything I'm doing for you right now should serve as like a really, really good positive tool to hopefully take on to your next classes. So, let's see. I just basically did that, and then compare this figure right here, this right here, exercise 11 with exercise 3, which is, where is that? Is that the same? Look at that. And now let's pull out our figure. There we go. Are those the same? Come on. Just regenerate it, whatever. Boom. Yeah. See? Now you can do, actually let me title this better. Using SS equations or controls toolbox. And then, see, that's your controls toolbox. This right here is the other one, the first half of the assignment. Oh, come on. Is that making sense? Pretty cool. There you go. So you can verify, oh my gosh, I know exactly what's going on, or are you just copying this? Alright, so now the next thing is using zero, pole, and DC functions, determine the system's pole, zeros, and gain. Take a look at the gain factor. What value appears? Let's see. Explain why the this gain factors appear via hand calculations. Analyze the transfer function at DC. What did I do here? Why did I say that? Oh, I know exactly what it's doing. Alright. So what I'm going to tell you guys, everyone. Okay. So assuming we, okay. So Dr. Stever mentioned this in class, and this is really, really important. Gotcha. So he said something in class where you can figure out the output. Okay. You can figure out the output based on looking at, let me think about it. You remember this h of t convolved with x of t, right? Remember that? You can solve for any type of system as the following. H of s is equal to s naught, some value like a pole, or actually not pole. So actually, how do I explain this? If your input x is equal to e to the, let's think about it, minus, do I want to do that? S naught t, right? Let's say this is like maybe some sinusoid, right? Some frequency, Okay, like 1 hertz or 10 hertz or something like that. Think about it, right? So if we throw a 10 hertz signal into our system, then what do we get? Here's like 10 hertz, right? So what do we get at the output? Y of t. Our output, we should ideally get the same 10 hertz signal, except with a different magnitude, and then e to the minus, we get the input back, s naught t, then I guess some plus some angle of h of s is equal to s naught. So any system can be analyzed like this. So for example, if we were to look right here, actually, like let's look right here, s is equal to I don't know, 10k, right? 10k, right? So if we were to look at this, here's 0 dB, right? If we go 1 decade above, here's this. What do we have right here? Minus 20 dB. Remember that? The slope is minus 20 dB per decade. Remember that? So that means our magnitude here is going to be, well, minus 20 dB, which converts to, come on. Oh yeah, this is where you can use Matlab as a calculator. So 10 to the minus 20 divided by 20. Oh, 0.1 millivolts. There we go. So if you threw a 1 volt, if you threw in a 1 volt input right here, 1 volt. Actually, no, how do we do it? X is equal to 1 volt e to the minus 10k or something like that. Just modeling that, or frequency, right? This should be a J or something like that. Think about it. That the output we would get 0.1 milli or 0.1 volt e to the minus j 10k, and then plus some phase. All right, because we know that the phase right here, if I were to draw the phase, I drew this bad again. 0, and then goes down like this. No, right here. That's the pole. Whoop. Here's minus 45. Here's minus 90. You guys like this messy stuff? There we go. Close enough. Oh, that should be there. Yeah, you know what I mean, right? So this is what he was trying to get to you. So what I'm trying to tell you is, what if we analyze y of t where our frequency, our s, is equal to dc, which is also equal to 0. All right? So that means all you're going to do for this condition is you're going to look right here. Okay? What's our dc value? What's the magnitude? What is h of s is equal to 0? What is that? That's equal to, well, 0 dB. But what's 0 dB? 1 volt. Okay? And then what's our phase right here? Our phase is, well, angle is equal to 0. Does that make sense? Easy, right? So that means our DC gain of RC filter is equal to 1. So that means the point is it's passive. It doesn't do anything. Well, it's going to be less than 1. The point is if you put a volt or a DC constant source into this, just pulse it, just DC like 1 volt for a long time, well, your output, well, it can't go up and it can't go down. It just sticks at 1 volt. Does that make sense? So another way of analyzing that is the following. I'm going to show you another way for. So H of S is equal to 1 over RC, S plus 1 over RC, right? So all you're going to do is H of S is equal to 0 is equal to 1 over RC, 1 over 0 plus 1 over RC, which is equal to 1. Here's RC, 1 plus, 0 plus RC. Then you can see how this goes into here to give you 1 DC gain. Make sense? Okay, prove it. Let's see, copy. Let's just copy the whole thing right here. Come on. Oh, come on. Boom. You guys getting your money's worth? No. It's okay. I like doing your guys' assignments. Run. So you know our RC circuit, right? We don't have any zeros, or if you look at back at this thing, we don't have any numerator S's. It's just a 1. So that means how many zeros do we have? We have no zeros. But we do have a pole, and that's at minus 1K. And then, oh, what's that? Our DC gain. Ah, makes sense? Cool? All right. See, there's our pole. That's our gain. Gain of 1 volt. Cool? And then let's look at the next part. PZ map. Generate a pole 0 plot. All right, do you guys really want me to do this? Yeah. Okay, I got you. Copy. And pole. Actually, nah, I'll let you guys do that on your own. All right, the one I really want to hammer right now is this. So, using the impulse function, you're going to generate an impulse response. So that means you're going to kick this box that we have right here. Okay? How do you do that in Matlab? Well, I'll show you. Actually, if you think about it, this assignment's way... I'm literally doing your assignment. But my job right here is to show you why we're doing this. So here's your time, right? And I picked 0 to 10 milliseconds. And here's your system. Here's your time. Run. Oh, I know why. Impulse response. Using SS equations. See? Oh, what's that 1,000? Ah, wait, have you seen that from before? Oh, you see? Okay, let me just title this. Impulse response. Part 1, something like that. See that's from the first part of the assignment. This is the second part of the assignment. Aren't they the same? Oh, except for that weird thing. Let me just make this 5. See? And then let me grab that puppy right here. Boom. Part 1 of the assignment, part 2 of the assignment. Are they the same? Easy, eh? And then let's look at this. Step function. Okay, so this is where the, let's see. Do I want to do this one? I'll let you do that on your own. No, please do it. Nah. I'll let you guys do that your own. But I will do the last part. And this is like the final closure of the analog lab. So, let me go back to here. Nope, not that. There we go. Make that bigger. So, the whole point of doing this is you can do a lot of stuff. You can build crazy powerful circuits, right? But now you want to know if these circuits are stable. Do they work? Like, can you see all these stuff or what's going on? So here's your system, right? Actually, y of s is equal to h of s, x of s. Remember that, right? So how do we do a step response? H of s, u of s, where u of s converts to u of t. Step response. Right? So, if you remember from the class, what is u of s? 1 over s, where you have a pole is equal to 0. Okay? So that means all you do is just h of s. That's it. Any system can be solved or check for stability. Check for stability. Also damping factor. And settling time, etc. So like EE360 stuff, okay? This right here is like probably one of the most powerful things. You can't really build an impulse, but you can build a step. And that's easy, just turn on the system. So how do you approach this? So equaling that, we do 1 over RC times 1 over s plus 1 over RC, right? That's our transfer function, right? Times 1 over s. Okay. Now we have to do that partial, what do you call it? Partial fraction expansion. What's this equal to? We have a pole here, and we have a pole here, so let's just do this. I'm going to call it a of s plus b of s plus 1 over RC, right? So there's a theorem called the Heaviside theorem. I think it's called Heaviside theorem. I think so. We'll figure it out. Where you can solve for this just by doing the following. You take your actual transfer function and then you multiply it by the pole. It's the pole, whatever pole this is, right? And then you analyze it at s is equal to, well, whatever pole it is, right? So this is going to equal to, well, this entire thing. Actually, not h of s. Not the pole, because that's going to give you this. Okay, no. Whatever h of s times x of s is, whatever this right here is, times that pole. So what I'm trying to say is, look at this right here, right? And then you just get rid of this. So all you're doing is 1 over s plus 1 over RC times 1 over s, and then times it by another s. See, this right here is that. This right there is this. This and this cancel out, and then all you do is just look at this, and then you just punch in s is equal to 0. So that means, what is this equal to? 1 over RC, which is equal to, there we go. I think so. Yes. I think so. No, wait, no. Is that right? No. I forgot this. 1 over RC. There you go. And then it becomes this. Oh, ignore that. 1 RC, 1 over RC. There we go, 1. So I accidentally forgot this. This goes right there. Here's that 1 over RC. It's 1 over RC divided by 1 over RC to give you 1. So that means this right here is 1. And then consequently, you can do the same thing with the other one. 5. And this one here is 6. Okay. So now for B, right? How do you solve for B, right? You look at the entire transfer function. I'm going to write the entire thing. Times 1 over S plus 1 over RC times 1 over S, right? Then you multiply it by the pole, whatever pole this is, right? And then you analyze the entire thing at whenever the pole goes to infinity. So that's at minus 1 over RC. Okay? Because if you punch this into here, that goes to infinity. So how do we get rid of this? Multiply it by the same pole. Boom, boom, done. And all you do is just 1 over RC times 1 over S. And then analyze this. S is equal to minus 1 over RC, which is equal to minus RC, RC. Make sense? Done. And now you can start solving for your actual output, the step response. Y of S is equal to the green marker 1 over S minus 1 over S plus 1 over RC. Easy? And now, if not the student, well, he will ask you for this. What is the output? So, by linearity, what is 1 over S? U of t, right? And then what is this? That's a pole. What's the residue? Residue is equal to 1, right? Pole is equal to minus 1 over RC, right? So all you're going to do is just put the 1 right there, right? E to the minus, here's the pole, 1 over RC, that's your pole, T. Don't forget the U of t, okay? Everything is stable. This is stable. Assume stable. Okay, it's always stable. RC circuits are stable. They won't blow up. Then you see that? You see that? And then what does this equal to? 1 minus E to the minus T over RC U of t. Boom. Does that look familiar? Just step response. So what happens when you input a volt right here, a step right there? Boom. As t goes to infinity, this goes away. You just get that 1. Make sense? So all you're going to see is this. So here's y of t, right? And then at your input, well, you'll get a 0 right here, right? But then it's just going to do this. Here's 1 volt. And that's it. And then this right here is 5 milli. Okay? So that's what we're going to expect. But I'm going to show you what we actually do. Instead of all that painful math, we're going to do the following. And yeah, you go ahead. You can do this. And here we go. Copy. And paste. So right here, I created let's do this. So right here, this is basically the equations, the actual equation for unit step in Laplace domain. Okay? So this is 1, this is a constant 1, and then this is an S, so 1 over S. So here's 1 over S. If you were to run this, F9, come on. Oh, there we go. There you go, 1 over S. There's your, here is your actual thing. Here's your transfer function here. And now, because we're doing state space equations, we want to create a state space like system. All you got to do is just take your transfer function and turn it into all this state space equations. And you get the following. F9. And there you go. This is how you model the unit step in the state space equations. Okay, so you see the painful math we did here. Where is that page? 6. Here's 5. See this painful math? You don't have to do this. Well, in hand calcs, yes you do. You need to know. But in Matlab, it does it for you. All you do is just this. Boom, done. And then since you know you're not doing a step response, which is this right here is a step response. You don't have to do anything. But we're going to teach you how to model any system. Just do this right here. Multiplication. H of S, X of S. Okay? Y of S. And then all you do is, okay, now you have a new system. Now kick the box. Here you go. Kick it on. Turn it on. Boom. What do we get? Boom. Ah. And there you go. You're done. All right. Does that make sense now? So that's how you do this assignment. It shouldn't be that bad. Hopefully everyone can, well, get this second half done. And then I will promise everyone, hopefully Friday we'll go over an example and prepare for your guys' review. So with that said, you guys should be done with this. This right here is the analog lab. You can have fun doing this assignment. And yeah, that's it. All right. Have a good day, everyone.